Find the first partial derivative of a function with respect to x or with y. The notation that we use here is let z equal to the function f of x, y, and so the partial derivative of the function f with respect to x is given in this form. And we use this notation. Or if we talk about the partial derivative of f with respect to y, we use any of these notations. And then for evaluation purposes, we evaluate the partial of z with respect to x at the point a comma b, and likewise to evaluate the partial of z with respect to y. Now for my remark here, I think is important to find the partial derivative of a function f with respect to x means to simply find the partial derivative, or to just find the derivative of the function with respect to x, and then you're going to treat y as a constant or coefficient. This is when you're looking for the partial derivative of the function with respect to x. In like manner, to find the partial derivative of the function f with respect to y, you find the derivative of the function with respect to y, and then you treat x as a constant or coefficient. Let's take these problems here to use that as an illustration to show you what we're talking about. So here the partial of f with respect to x is equal to, I'm focusing on x, and then we're going to treat y as a constant or coefficient. So this partial derivative is just 2. Y is treated as a number. The 3 is a number, so their derivatives would be 0. The partial derivative of f with respect to y, I look at where y is. X is a constant, 3 is a constant, so their derivatives are 0. The derivative of negative 5y is just negative 5. The next one, the partial derivative of f with respect to y. Here, the y cube is treated as a coefficient. So take the derivative of x squared, we just get 2x times its coefficient, y cubed. The partial derivative of f with respect to y is 3 times x squared is a coefficient, times y to the second. The partial derivative of z with respect to x is just the square root of y. Here the square root of y is the coefficient of x. And then the partial of z with respect to y, so we look at the derivative with respect to y, and so that gives us 1/2 times x times y to the 1/2 minus 1, negative 1/2. And so we can write this as x all over 2 times the square root of y. Take the partial of z with respect to x. That gives us 2x minus 4y. The partial of z with respect to y is negative 4x plus 6y. Now you can expand this if you wanted to. You don't have to, but I think it may make finding the derivative a little bit easier. So find the partial of z with respect to x. We look at the derivative of the natural log of x, which is 1 over x, times the derivative of x, which is just 1. You just get 1 over x. Y is treated as a constant, so the derivative of a constant is 0. The partial of z with respect to y, in the same fashion, x is a constant, so it's 0, and this is minus the derivative of the natural log of y is 1 over y. The partial of z with respect to x is 1 all over x squared plus y squared times the derivative of x squared plus y squared with respect to x. That's just times 2x. So what we have is just 2x all over x squared plus y squared. The partial of z with respect to y is in that same fashion. So we have symmetry, so it's just 2y all over x squared plus y squared. This is a little bit more into it. So we take the partial of z with respect to x. We use the quotient rule. So the derivative of the numerator is going to be 1 times y times our denominator minus the numerator times the derivative of the denominator with respect to x. So that's just times 2x. And that's all over x squared plus y squared to be squared. We simplify this, we get x squared y plus y to the third minus 2x squared times y, and that's all over x squared plus y squared to the second. And we simplify this, the partial of z with respect to x. We'll just write the y cubed first, since the coefficient is positive, and this is minus x squared y all over x squared plus y squared to be squared. Now I'm going to go out on a limb and tell you that the partial of z with respect to y, because this function is symmetric with x and y, and x squared plus y squared. So I'm going to surmise that this partial is going to be x cubed minus x cubed minus x times y squared all over x squared plus y squared to the second. But let's find it, just to be exact, right? So you don't have to, when you're doing these problems, you find one, since it's symmetric, x times y, right? X squared plus y squared. Then I bank on that. But we can go through the steps. The partial of z with respect to y, we use the quotient rule, so this becomes x times the denominator, x squared plus y squared, minus the numerator times the derivative of our denominator with respect to y, that's 2y, and that's all over x squared plus y squared to be squared. So we get here x cubed plus x y squared minus 2x y squared, that's all over x squared plus y squared to the second. We simplify that, and so that gives us x to the third minus x y squared all over x squared plus y squared to the second column. They look to be the same. Found the partial here of f with respect to x. This is 1/2 times parentheses x squared plus y squared. This is the 1/2 power minus 1, so this is negative 1/2 times the derivative of the inside with respect to x, that's 2x. So we end up with x all over the square root of x squared. Let's see, erase the whole thing. X squared plus y squared. And the partial of f with respect to y, again, looks like symmetry with this function. So this is y all over the square root of x squared plus y squared. Thank you.